try to report on joint work with Sasha Efimov and Ludmil Katzarkov, where we try to develop a version of Lagrangian Floer theory for trivalent graphs, as you will see, to understand a new perspective on mirror symmetry for curves. So what's the problem here? So mirrors of curves are kind of one of the most trendy examples in, there's lots of work on homological mirror symmetry for curves in various directions. But so I will start with a construction that starts from a curve given as a hypersurface in, let's say, either C star squared or in a toric variety, and produce mirror to it. And in fact, one should consider non-Archimedean curves. So in fact, it's going to be defined over a field K, which for me, a Novikov field, but you could probably use some other non-Archimedean fields as well. And there's an algorithm which, given a defining equation for a curve, produces a mirror Landau-Ginzburg model, a toric Calabi-Yau, together with some superpotential. And I mean, this is sometimes called the Hori-Vafa mirror because they were the first to propose something of this sort. Maybe in the opposite direction, but anyway. So there's a concrete construction, which I'm just putting here for completeness. You don't need to worry about it for this talk, which says, given a Laurent polynomial, you can produce a piecewise linear function called its tropicalization, which looks at basically the valuations of f in terms of evaluations of the variables. And then from there, you can produce a polytope, which is everything that lives over the graph of this tropical piecewise linear function, and treat that as a moment polytope for a toric Kähler variety, and then define a function on that, which in the case that your hypersurface was just in an torus, it's just a single toric monomial. Otherwise, there's a sum of terms indexed by the divisors of your variety. So the simplest example of something like this is if I start with a pair of pants, which I choose to write as defined by the equation 1 plus x1 plus x2 equals 0, where x1 and x2 are assumed to be non. Then the tropicalization of that becomes the max for me of 0 and the valuations of x1 and x2. This is going to be piecewise linear equal to 0 in a quadrant, C1 and C2, the two variables on the other side. And the moment polytope you get out of that is in fact congruent to an octant in space. So that the mirror you get, in this case, would be C cubed with a product of the coordinates. The critical locus of this function is going to be just the union of the coordinate axes. So to check homological mirror symmetry for the pair of pants would mean, for example, comparing coherent sheaves on the pair of pants with a certain Fukaya category of this Landau-Ginzburg model, which somehow is supposed to probe the critical locus, the singularities of this function W0. But the theme we'll develop in this talk is that we should think of maybe this critical locus itself, rather than the ambient space, as being the space on which we want to do geometry on the mirror side.
So does it mean that it's sort of a local to global principle for Landau-Ginzburg, that you look for the neighborhood of the critical locus? Something
so it's some sort of local to global principle, which is false, but I'm going to claim that up to some corrections, which are easier to ignore, there's something like that. So maybe for comparison, right? If we were instead comparing the symplectic geometry of a pair of pants with the algebraic geometry of this Landau-Ginzburg model, we would be talking about, say, the derived category of singularities defined by Orloff, or matrix factorizations of a superpotential. And there are results saying this only depends on a formal neighborhood of the critical locus. So the slogan is that in symplectic geometry, this is true up to the fact that there may exist corrections from basically rational curves in Y, which hit the critical locus without being contained in it. Now, in the case of, this case here is just affine space. There's no rational curves in there, so that would be safe. There's no corrections. But maybe the correct statement would be that the critical locus, possibly with a correction to its A-model parameters coming from this reduction, should be equivalent in a certain sense, when equipped with suitable data to the total space.
Yeah, it's some analogy in the module story that you should take into account Stokes phenomenon in order to make things equivalent, the Ram and Betty. Okay.
Yeah, but here it's kind of simpler because Y is always toric, and so instanton corrections on toric varieties tend to take a really simple. The structure is simple. The numerical details are formidable because there's all these Gromov-Witten generating series, but the structure of the corrections is fairly simple. All right. So second example, just for context, is if I look at an elliptic curve defined, say, as I start from equation x1 plus x2 plus t over x1, x2 equals constant, say, inside the algebraic torus k star squared, and I compactify to a suitable toric variety, this will be, in fact, an elliptic curve. And the construction gives a mirror, which is, in fact, the total space of the anticanonical bundle of P2 with some superpotential, which is whatever it is. But the relevant thing for us is this thing has Morse-Bott singularities along a smooth cubic elliptic curve in P2. And that cubic is the usual mirror to this elliptic curve here.
So just for graduate students, Morse-Bott means that it's kind of a Morse, but non-isolated critical points.
That's right. That's right. So Morse-Bott means the critical locus is smooth, and at every point in the normal directions to the critical locus, the Hessian, the second derivatives, are non-degenerate. And in fact, in this example before of C cubed, also the singularities are Morse-Bott except at the origin. The smooth part of the critical locus is not too nasty. All right. Oh, what is T in this term? It's a parameter which, what can I say about this parameter? So I am going to be interested in the symplectic geometry of this thing, so it doesn't matter to me. But if I were doing algebraic geometry on Y, it would matter to me which elliptic curve in the Fermat pencil this is. And that would determine a complex deformation parameter for this elliptic curve. T, if you want, is a parameter that has to do with the symplectic area of this compactification of this open elliptic curve. It's actually not relevant for this talk, so maybe I should just have abstained. Anyway, it's a constant. Okay, so the next example, which is closer to where I want to get, if I have a curve of genus G at least 2 in a toric surface, then there's again a construction that gives a mirror. And what happens is, no matter how you choose the details, the critical loss of this superpotential always ends up looking the same. It always ends up looking like a trivalent configuration consisting of 3G minus 3 CP1s meeting in 2G minus 2 points where 3 of them meet together. So for example, the mirror of a genus 2 curve, there are various constructions there's one appearing in the work of Seidel, one by Katzarkov, KKOY, Katzarkov, not Kontsevich, wait, Katzarkov, Kapustin, Orlov, Yotov. There's one in my work with Abu Zaid and Katzarkov. There's some in the work of Gross, Katzarkov, Rodat. Anyway, Ludmil with many different people. They mostly end up all having critical loci which look like this. All right. And so, okay, so that's kind of, I can't resist. There's Jeff Koons has these sculptures of giant balloon dogs, which are kind of the best, real world picture of these things you can come up with, even though they're not trivalent, so don't look too closely. But picture aside, what's supposed to happen near each of these points is that the model looks like C cubed with a product of the coordinates, so like the mirror of a pair of pants. And the way that tropical geometry conspires to produce these mirrors, in fact, each of these charts where this shows up is in correspondence with some pair of pants in a pair of pants decomposition of our curve on the other side. So in fact, a large complex structure limit degeneration, or if you want a non-Archimedean / tropical limit of a family of genus G curves, induces a pair of pants decomposition on their complex realizations. And this pair of pants decomposition is reflected in the structure of the mirror. So the question is, what can we do with this? So, sorry, I missed something. So one thing we can do, okay, so we would like ultimately to prove homological mirror symmetry. And the direction I want to talk about here is the one that compares coherent sheaves on my curve, viewed as maybe as a hypersurface or not, to some Fukaya category of the mirror. So the natural and normal thing to do is to just take this Landau-Ginzburg model, which is a threefold with a superpotential, and define some fiber-wise wrapped, partially stopped, something Fukaya category, which looks at Lagrangian submanifolds in the total space. And that has been done, for example, by Catherine Canezzo for genus 2 curves. You can compare these categories, get to homological mirror symmetry statements. I have a long delayed paper with Abu Zaid. It will actually exist at some point. It is in progress. That does this also for curves in C star squared and so on. But, okay, so if you were to look at how this works, for example, for the pair of pants, you would start looking at the symplectic geometry of C cubed with a product of the coordinates. And then you need a Lagrangian submanifold in there. And there's many interesting Lagrangian submanifolds in C cubed, but the one you would like to really get to is the mirror to the structure sheaf of a pair of pants. And that one is surprisingly unpleasant to find until you know what you're supposed to do. So the simplest way I know to describe the Lagrangian submanifold in there that does that is to observe that the of this map are C star squares. Right? Because if you set the product of the coordinates in C cubed equal to a constant, you get C star squared. Especially, say, above -1, this is Z1, Z2, Z3 equals 1. This has a real positive locus. I will call L0 the Lagrangian in here formed by the points with real positive coordinates. And then I can transport this over an arc. This is a symplectic fibration, this map from C cubed to C given by the product of the coordinates is a symplectic fibration. So I can produce, in fact, a Lagrangian submanifold of C cubed by just moving this L0 in families over some arc in the base. And then Floer theory for L0 with itself would involve pushing L0 by certain perturbations, which in the fiber correspond to something called wrapped Floer homology, produces infinitely many intersections. In the base amounts to wiggling this arc to create, in fact, to push its ends past themselves, so you create two intersections. And then, there's a lot of technicalities. The current draft of that paper is like 70 pages and still growing. And at the end of the day, you find that the Floer homology of this Lagrangian with itself is isomorphic to a quotient of a ring of Laurent polynomials by the ideal generated by 1 plus x1 plus x2, which was exactly the defining equation of our pair of pants.
Just to be sure about notation, this L capital 0 is Lagrangian in the total space obtained by moving L small. Okay.
That's right. L0 is obtained by parallel transporting the little L0, which is two-dimensional, along a U-shaped arc.
Yeah, and whatever Fukaya Zeidelech Landau give, anyway, the Fukaya version of the category you consider, it's just definition analogous to the Paul's book. Yeah, you consider.
So it's something analogous to Seidel's book, except these Lagrangians here are not fiber-wise compact. And so besides a bit of perturbation in the base as in Seidel's book, we also need to introduce a wrapping perturbation within the fibers.
Mm-hmm. And okay, so then for this L capital 0, the wrapping, the definition of the wrapping is more complicated because it kind of takes care about two directions to infinity.
That's right, but it's basically done fiber-wise. It's wrapping within, so there's a perturbation in the base as in Seidel's pictures, and there's a perturbation in the fiber which is wrapped Floer homology in C star squared.
Mm-hmm. Okay.
So inside this fiber here, the self-wrapped Floer homology of the fiber-wise picture will look like Laurent polynomials in two variables. And in that fiber where they re-intersect, there's going to be another copy of Laurent polynomials in two variables. And then the hard part of the calculation is in fact counting holomorphic disks that live over this shape. Anyway, so one can get there, but it's not fun. So the goal of it is not to do this, it's to do something that's maybe less conventional, maybe less well justified, but seems much more practical. And I would like to argue basically is interesting to study. Okay, so I will escape this and instead tell you, well, the problem with that, there's several problems. One of them is that the choice of how you embedded your, say, your pair of pants or what you were trying to see inside some ambient space plays a key role in the geometry. And so it's not clear why this is intrinsic in any way. And but at the same time, because the locus always seems to look the same independently of the ambient space, this is maybe where one should work. That would also save us from having to visualize three-dimensional Lagrangians in a threefold. We would like to just go back to dimension one. So
does it mean that you produce global Lagrangians in your capital Y by looking at something, the critical?
That's what I would like to claim. In practice, I do not know how to do this.
Because
so yes, things are too singular. And anyway, so I'll comment on that pretty soon. Yeah, I'll get back to this. To what does it mean? I'll try to explain a bit of what it means. So to explain what it means, I need to tell you about Lefschetz thimbles and the analog in the Morse bot setting, where we don't have these singularities beyond, where the singular locus is smooth. So remember I told you there's one way to use this construction, say for an elliptic curve, and obtain a mirror, which is one of these toric threefolds with a function, where the singularities just show up to be Morse bot curve. So that means you have a smooth elliptic curve worth of critical points, and in the normal slices to it, you have something that looks like a quadratic form, is the local model for your function. So in that case, there's a dimensional reduction which follows what happens in Seidel's work on Lefschetz vibrations, on the case where you just have a Morse singularity. If you have a Morse singularity, then what Seidel tells us, and of course many other works have bet on that, is the singular fiber is obtained from the smooth fiber by collapsing something called a vanishing cycle. And over a path in the base connecting the critical value to a smooth regular value, there is a Lagrangian called the Lefschetz thimble, which traces how the vanishing cycle in a smooth fiber collapses to the critical point. This thimble is a Lagrangian and therefore an object of the Fukaya category that we study. It is, in fact, in that case, it's an exceptional object. And that's because if I push off a thimble away from itself, I end up with one intersection at the critical point. Now, if I have instead a stratum of singularities along a smooth critical locus, this Morse-bot setting, then there's a similar story, but starting as input with a Lagrangian inside the critical locus. So that means given a closed curve on this elliptic curve, let's just see this it's an elliptic curve, but let's call it a torus now for a symplectic geometer. And then there I take a loop, and then out of that loop, I can produce a Lagrangian solid torus, in fact, inside the total space, in such a way that if I push it by my formulas, by my recipes for computing morphism space, all the intersection theory reduces to inside the critical locus. And so that means the Fukaya-Seidel category of this big three-dimensional thing reduces to the usual Fukaya category of this elliptic curve. And that's not surprising because that elliptic curve is the usual mirror, the one that sane person would have used instead of this crazy construction. So, in fact, there are similar constructions for sufficiently simple Riemann surfaces, but you will not get past genus 1 unless you go into stacky things where symplectic geometers are completely lost. At least I'm completely lost. So just to point out that there are things that have similarly one-dimensional mirrors you can try to study, but that's not something I will do. If I try to do a similar construction, at least two, then one lands in pretty exotic territory where I wouldn't know how to associate a Fukaya category to whatever I can produce. So the goal of the construction I want to explain today is to remedy this, to figure out what can we do along these lines to associate a Fukaya category to the critical locus in a way that we hope reflects the Fukaya category of a threefold inside which this happens.
Will you have this equivalence, which is in your red box in your construction, or just two functors?
So the equivalence is a corollary of two different proofs of homological mirror symmetry. So no, the answer is we do not know how to prove this directly. The only way right now that I know how to prove the equivalence is by proving separately that both of these Fukaya categories are equivalent to the derived category of the curve on the other side. I'm currently trying to remedy this, at least for simple examples. One of my students, Jae-won Chang, is trying to work on his thesis project is exactly about trying to make this more precise and understand more of the foundations. So, no, in some sense, the results I'm going to tell you about soon are slightly unfinished in that it gives a candidate story. That story is very compelling. It works in that you can prove homological mirror symmetry, but I don't have a complete proof that it accurately reflects the geometry of a threefold.
Excuse me, Denis.
Yes?
Is this statement about the Morse-bot singularity and true for higher dimensional mirrors as well? So if you take your prescription...
Under suitable assumptions. The main assumption is that inside the zero fiber of your Morse-bot vibration, you don't want to have rational curves which hit the critical locus without being contained in it. And that already fails actually to some extent in this example. So then you need to understand how they induce corrections to the mirror map and so on. So that statement actually needs to be corrected to account for rational curves.
So sorry for stupid question because I forgot. In the conventional story of Seidel, if your singularity is not of Morse type, can you still reconstruct global Fukaya-Seidel category from local considerations? Just
well, yeah. I mean, so Seidel doesn't define things outside of the Morse case.
Maybe some other people who can.
But I mean, so I think the answer is the whole theory is still partially a work in progress. The most elaborate work on this is maybe for exact, in the case where the manifolds are affine, for example. Then I would say Ganatra, Pardon, and Shende have this theory of Liouville sectors that give a lot of structural properties. But anyway, the answer is yes and no. I mean, things are determined by the critical locus and the Floer theory of Lagrangians in the critical locus, accounting for holomorphic disks that may be in the ambient space. Yeah, so the Lagrangians come from the critical locus.
Okay, yeah, all right. Understood.
But their Floer theory may be deformed by the ambient space. But I don't think you can find this statement written anywhere in this level of generality. All right. So anyway, I want to try to get to a different part of the story because this is all motivation. But eventually there's just going to be pictures with trivalent graphs, which are more fun than trying to kind of understand complicated three-dimensional spaces and things. So the question basically is we would like to understand how to define a Fukaya category for some kind of trivalent configuration of Riemann surfaces. And mostly I have in mind P1s or possibly just copies of a complex plane C to handle the case of mirrors to non-compact curves. Right? I mean, it depends whether I want a projective curve or a quasi-projective curve or something to begin with. I guess I should say affine since whatever. Okay. And okay, so the naive construction that I would like to propose is we think we know what skyscraper sheaves of points correspond to. We believe that skyscraper sheaves of points, especially the ones that are kind of near the thin part of an non-Archimedean curve. I mean, the point valuation is not one of the, is generic, basically, are mirror to circles that live inside these P1s or A1s that form our configuration on the mirror side. And so that means, so this is kind of consistent with, say, as about Strominger-Yau-Zaslow, T-duality, torus vibrations, and so on. But so that means now that a line bundle should be a Lagrangian whose intersection number is 1 with all of these families of circles. And so how do I produce a Lagrangian which intersects every circle once? Well, the answer is I probably want something that looks like a graph connecting special points of each component. So I forgot to say I mean, this trivalent configuration meeting in nodes, the nodes, in fact, there's exactly 2 nodes on each P1. Okay, and so maybe the idea I want to have is that I will try to define a Floer theory for a trivalent graph like this L0, passing through every component of my configuration in such a way that if I try to intersect it with a skyscraper sheaf of a point, I will find a one-dimensional space. And now if I want to understand, for example, functions on a pair of pants, that's a good place to start, then I need to have this trivalent graph on a union of 3 copies of C. And I want to do some kind of wrapped Floer homology, which means I will intersect it with its push-off that spins around at infinitely many times. And I will look for intersections, and I will do something And I'm hoping that at the end, I will get something that's like the ring of functions of a pair of pens. Okay. So
and home from this green whatever graph with your circle LP, it will
it will be just rank 1 here. It will be rank 1. It will be like the home on the structure sheaf, the skyscraper sheaf.
With the okay.
All right. So that's the goal, and so okay. I think I'm not going to talk really about that, but maybe I'll say just a few words, and then we'll go back to the pictures with graphs. But since I sense lots of pending questions about what does it mean and how does it relate to the threefold. So the problem we have really is we would love to say that the mirror, remember I told you about this Lagrangian in C cubed, which is mirror to the structure sheaf. And we would love to think that we can kind of squish it into something like a thimble, something that lives over an arc coming out of a singular fiber and obtained by parallel transport of things that collapse to some configuration in the critical locus. So one of those thimbles. And this really works for the mirrors to skyscraper sheaves of points. The mirrors to skyscraper sheaves of points, you start from a circle here, and you parallel transport it to get a thimble. And that is indeed how you produce mirrors to skyscraper sheaves of points. But for the structure sheaf, all we have is this strange U-shaped thing built from R plus squared. If we allow ourselves to suspend this belief and allow a singular Lagrangian, something piecewise smooth, then we can do it. It is true that there is in fact some piecewise smooth approximation to a Lagrangian pair of pens in C star squared, which collapses under parallel transport to this trivalent graph. So there is some non-smooth Lagrangian in C cubed, which ends up on this trivalent graph here, and it's just not smooth anywhere else. However, the thing that plays the role of a vanishing cycle, this configuration that we see in the smooth fiber, does have a Lagrangian smoothing that is understood. It's something called the tropical Lagrangian pair of pens, and it was constructed 2 or 3 years ago simultaneously by Matesi, Michalkin, and Hicks in 3 different papers. So in fact, there's probably at least 4 or 5 constructions of it. And so the slogan is that probably what you should imagine I'm going to tell you about Lagrangian Floer theory in this critical locus really has to do with Floer theory for this vanishing cycle and its relation to the Lagrangian in the total space C cubed that nobody can see really in this shape of a thimble, but some other Lagrangian exists. We just don't know how to think of it. I mean, well, we know how to think of it for this U-shaped construction, which doesn't look at all like it, but you can show is Floer isomorphic. So secretly, those pictures that I will draw should be computing. In fact, there's a slogan that this is computing the degree 0 part of basically 1/2 of the Wrap-Floer cohomology of this Lagrangian. But I'd rather do it in the language of trivalent graphs because I think this is where the pictures should be drawn. All right, sorry, so this is all the motivation part. At some point I should actually give the construction. So, but I need to tell you about another feature of this which will be surprising. Because the construction has some weirdnesses, and I want to point out this weirdness is necessary. So if we want to think of how Floer homology for this graph L0, just a union of 3 real lines, radial lines in 3 complex planes, are going to intersect and produce a Floer homology. So I'm going to push each of these radial lines counterclockwise infinitely much. This will create an infinite sequence of intersection points. So the self-Floer complex of L0 has 3 infinite sequences of generators in the cylindrical ends, and some here at the vertex. A posteriori, I am telling you there is 1 generator at the vertex. This will be part, I don't have to explain it now because this is a definition I'm going to make anyway. But the claim is this is the right answer. And now these generators together should give a basis for the Floer homology, which means they should give an additive basis of the ring of functions of a pair of pants. We have a problem already because there is no canonical basis for the ring of functions on the pair of pants. There's choices involved. So, but nonetheless, you can ask which kinds of functions, what do we know about them? So the next thing we know is that we can evaluate these functions at points, and we can at least find their valuation at a point of given valuation. The observation is if I have a Floer generator like this one, so it's supposed to be a function on the pair of pants. If I want to find its value at a point of a pair of pants, a point is mirror, a skyscraper sheaf of a point is mirror to that. Well, if I have a function, I can think of it as a map from the structure sheaf to itself. Evaluation at a point is a morphism from the structure sheaf to a skyscraper sheaf. And the structure constant of this composition in my category is supposed to be the value of a function at the point. So transcribing this to Floer theory, it says there is a Floer product given by counting holomorphic triangles. Well, here there's only one, this one shaded in orange, weighted by its area. So you have a coefficient whose valuation will be, in fact, the symplectic area of this orange thing. And that's supposed to be the constant that you're computing. So what this shows, and in fact the analogy is clear when you compare with wrapped categories of other surfaces, is that the generators in these cylindrical ends should be successive powers of a given function. So this is some function, this is its square, this is its cubed, and so on. And these functions should have basically a pole at one of the punctures of our pair of pants. So what we want is an additive basis of this ring of functions consisting of powers of meromorphic functions on P1 with a single pole at one of these 3 points. So fact, no matter how you choose 3 rational functions on P1 of degree 1 with poles respectively at 0, -1, and infinity, the constant function 1 and powers of these functions you choose are an additive basis of a ring of functions. Why? It's basically partial fractions decomposition for any rational function with poles at those 3 points. But as far as I know, there's no canonical choice of these local coordinates, or if you want, of these rational functions of degree 1 with prescribed poles. You need to choose, you know where the pole is, you need to choose where the 0 is. And this actually has to do with some lies in what I'm telling you about these Lagrangians, these circles corresponding to points. There's a choice needed to make one of these circles. Once I turn it into a Lagrangian in C cubed, it is obstructed, and there's a choice of bounding cochain needed. I mean, there's choices into how to make this into an object of a category. So the goal of the reduction to the critical locus is, in fact, to evacuate all of these corrections coming from holomorphic disks and just try to focus on the algebraic structure and get rid of instanton corrections that we don't actually want to look at. At the same time, it means that this is not reflecting on the nose the symplectic geometry of the ambient space with this particular critical locus. There are deformations of the Kähler parameters. Okay, so here's another problem. Let's take now a function that lives here on the pair of pants. This Floer. I want to evaluate it at this point. Well, in usual Floer theory, I would start looking for holomorphic disks that start from this thing, and then go either this way or that way, and then they live on this component, and they're supposed to somehow close up to a triangle with the last edge on this loop, L sub p. Well, that doesn't exist in usual Floer theory, but I know that whatever function this represents, it's not going to vanish identical an open subset of points. Right? The zeros of any rational function are discrete, sorry, non-zero rational function. So this must have a way of evaluating in a non-trivial way against this Lagrangian. So that tells me that holomorphic disks on these pictures need to be able to pass through the trivalent point and come out on another component. So there needs to be a process for holomorphic disks to propagate through the trivalent point. Okay, so that's this. All right. So with that in hand, now I'm at a point where most people would have stated a theorem. I'm not even going to do that, but I'm going to state a definition at least. 40 minutes into a talk, I should at least have a definition. So here are the data that go into defining a Fukaya category for this kind of configuration. So start from something I will call a configuration of P1s possibly and A1s with these triple points, and each P1 has two special points like that. Each A1 has one. I can actually define it for more general trivalent configurations, it's just that this is the only case that I care about. So the data consists of, I need to have a symplectic form. The main parameter here is the area of each component. Okay, by symplectic form on this, I mean on each component. This may also carry a B field or a bulk deformation, which means the weight that I would assign to this rational curve would not be just, say, q to the AI, but could be some other element of valuation AI in my field. And then I'm going to have something I call chart data at each vertex. So what is the chart data? Well, in keeping with what a slide about the ring of functions of a pair of pants, it's the choice of three functions. For each vertex, I think of some abstract pair of pants, a P1 minus 3 points, and I choose three functions which are going to extend on this pair of pants, which extend to meromorphic functions with a single pole at the respective puncture. So my punctures are infinity 0 and minus 1. The nicest functions I can write are just the ones which have a pole at one of these and a 0 at another one of those. And observe, these are all expressions that somehow, if you expand them, they're coefficient free. So that tells you, life, there's something fair in life, in this line of business, when there are no coefficients, no numbers that come up. I still have minus signs because I think I messed up my signs. Efimov tells me that I should really stick to 1, not minus 1. Okay. So what is the interpretation of this data? Near a maximal degeneration, a non-Archimedean curve of genus G is in fact a smoothing of a maximal nodal configuration, which is built from basically a union of P1s glued together each time in 3 nodal points. Okay, so I should think of this as really, the classical topological story is a Riemann surface can be degenerated into a union, so it can be decomposed into a union of pair of pants topologically. The correct algebraic geometry way to think of this is there's a degeneration to a nodal curve formed by squishing each of these loops to a point, and that nodal curve now will be a union of P1s, each with 3 marked points to each other at those points. So now, if I want to understand how a smooth genus G curve can be recovered from this by smoothing, one way to do that is to declare, okay, I will choose some local coordinates on these P1s near the marked points, and I will declare that the nodal configuration was product of the two coordinates, calling yi and y prime I, the coordinates in the two components, with the product of those equals 0. That's a nodal union of two coordinate axes. And I will deform that to yi y prime I equals a non-zero constant.
So that's the data which allows you to lift from the skeleton to the actual holomorphic curve.
This is the algebraic geometry side. I'm describing a procedure. This is.
I mean, it's a mirror to that construction.
So this thing is mirror to this thing. So my symplectic manifold is a union of P1s with triple points. Each P1 has 2 points on it, which are where 3 P1s attach. Instead, I want to say, for you, probably I should just say, this is my feeble attempt to explain a non-Archimedean Tate curve. Okay.
In symplectic terms.
To symplectic people. No, this is the algebraic geometry of a non-Archimedean Tate curve.
Yeah, okay, good. Yeah, it's not necessarily, yeah, right, yeah.
Okay, so, except I don't know what that means exactly, because, I'm not an algebraic geometer. But so, from a naive perspective of what a symplectic geometer would say about what this thing is, it's a chart. It's a chart on a neighborhood of a large complex structure limit point in the moduli space of genus G curves, where you realize smooth genus G curves by smoothing a nodal one. One way of explaining how you smooth is that you delete these points, and then you glue local charts by saying this coordinate become proportional to the inverse of that coordinate. Okay, and the smoothing parameter tells you what's the coefficient, what's the size of the neck would be what a topologist would say. Of course, non-Archimedeanly, this AI now becomes the length of the valuation, in the valuation, that's the length of the leg of the tropical curve. Okay. And leaving the world of things that are stable and reasonable curves, I might even want to think of this instead as taking a nodal configuration where I have these extra P1s in the middle, which really serve no purpose except to give me a handle on this where I do the gluing only one side at a time. So I insert just some stupid component in the middle to save me the trouble of talking about local coordinates on 2 of these P1s at a time. Anyway, so now you see that this chart data comes up in the choice of how I perform this gluing, because I have to choose which local coordinates I will use to kind of describe this process of identifying. The correct thing to do probably would be to take affinoid domains inside these non-Archimedean P1s, non-Archimedean pairs of pants, take affinoid domains and glue them by overlapping the coordinates on some leg with this amount of length inserted. But the point is, this depends anyway on the choice of a coordinate near the end of a pair of pants. All right. So returning to the symplectic side. So an object of my Fukaya category of line bundle type will be a trivalent graph with one arc on each component, and I will force a fixed tangent direction at the vertices. That's just out of laziness. And if you want really to have a complete story, you should consider these trivalent graphs together with local systems over them, trivialized at the vertices, as a way of having more objects. The space of objects, if you just look at these graphs up to Hamiltonian isotopy, there's a few real parameters measuring amounts of areas and some discrete parameters about rotation numbers. And what that measures is things like the Chern class of a line, the degree of a line bundle, and that measures also basically its position in the tropical Jacobian, but just the valuation. And if you want to specify a line bundle, a non-Archimedean line bundle, rather than just its, the valuation of its image under Abel Jacobi, then you also need to insert local systems. to define homs between two such objects, we will use a Hamiltonian perturbation to make sure that our Lagrangians are not on top of each other near the vertices. And the rule will be that near the vertex, we will rotate the legs slightly counterclockwise. Also, if we have some non-compact ends, we will wrap at infinity. So for example, the self-homs of L0 on, the L0 on each of these pictures. So this one is the mirror to a once-punctured elliptic curve. Anyway, I will push this blue thing to the red thing by going slightly counterclockwise near the vertex. And then here I have a non-compact end, so I wrap at infinity. This one is the mirror to a closed genus 2 curve. I will just push a little bit, again, counterclockwise in every leg near every vertex. And of course, there need to be other intersections. Then with this understood, I have Floer complexes generated by intersection points between those Lagrangians after push-off. They have degrees 0 or 1, depending on whether things are intersecting slightly clockwise or slightly counterclockwise. Additionally, I have these unusual intersections at the trivalent vertices, and I declare those to be a degree 0 generator. So each vertex becomes a degree 0 generator, the other intersections as usual. So in this example, here on this punctured elliptic curve, hom from L0 to itself, this would be actually global functions. Right? This is hom from the structure sheaf to itself. There's a generator in degree 0, one in degree 1, and infinitely many more in degree 0. So I have a model which is not minimal. I mean, after passing to cohomology, there's no H1, and H0 will be infinite rank. On the genus 2 curve, I have two generators, it's mirror, I have two generators in degree 0, 3 in degree 1. You can check, relatively quickly things like Riemann-Roch formulas, at least just from numerology of how many times things intersect. Okay, so the interpretation of what's going on here is you should think of a line bundle on the algebraic curve as built by gluing together pieces, which are, so this prescribed piece near a vertex corresponds to just O on a pair of plans of my decomposition. And whenever on a leg I have some twists with K-turns, this one doesn't twist, but if I instead chose my Lagrangian to zigzag around one of the components of a trivalent configuration, that would amount to inserting a line bundle of degree K on the corresponding P1 neck piece. Or if you prefer, if you don't like the P1 neck pieces, in this gluing here, it's the fibers of those line bundles are identified with a twist that inserts degree K.
And if you have a C component?
If you have a C component, then it's just, it's just there, it's O. That corresponds, the C component just corresponds to, having a piece of a pair of plans where you don't glue anything. So you're going to just puncture this point and not glue anything, and we just have O. And the wrapping is just something that shows up in symplectic geometry at the non-compact ends. You shouldn't obsess over the wrapping part. I mean, I guess you could say, you could also say this wrapping corresponds to allowing arbitrary pole orders at this puncture, basically. Right? It's the process of saying that functions on the complement of this point are a limit of meromorphic things with arbitrary pole orders.
Okay, so now infinity structure or what?
Yes, infinity structure coming. So there's differentials and products and an infinity product on these morphism spaces. As usual in Lagrangian Floer theory, we count holomorphic disks with boundaries on our Lagrangians. There's one change, which is that we allow our holomorphic disks to propagate through the vertices. So for example, the Floer differential normally would just count one holomorphic disk with boundary on one Lagrangian A. Sorry, I've changed the names to A and B. One boundary on A, one boundary on B, connecting two intersection points, like a bygone, like that, inside my picture. Now instead, I allow chains of such things jumping from component to component through the vertices. So for example, this map from a union of two disks to this configuration with a disk here and another disk here contributes to the coefficient of, in this case with my conventions, a differential from x to y. You can ask, well, how much does it contribute? So we need combinatorial rules for what happens when we pass through a vertex. And the answer is, first observe, because of how we chose our perturbations, incoming pieces of holomorphic disks, I think of them as propagating from the input towards the output. From the input, they come in with a certain degree, because these tangent directions, these things are tangent to each other at the origin. There's a certain covering degree of this disk. At the output side, there's also potentially a degree, but it might be 0 if this is a very thin strip. The input degree is always at least 1. So the statement is that this chart data tells me a combinatorial coefficient for what happens here. It says if the input has some degree, in this case, and the output has some output degree, in this case 0, what I'm supposed to do is I take the input variable, the input coordinate, P1, associated to this leg, to the D1. This is a meromorphic function with a pole of order D1 at this puncture. In particular, it is regular near that puncture. Therefore, I can expand it as a power series in the inverse of P2. And I want the coefficient of P2 to the minus 1. So for example, in the above setup, let's say that the input coordinate, this point is minus 1, and we choose this input coordinate, and the output point is 0, and we choose this coordinate. Sorry, by coordinate I mean inverses of coordinates. I would take this function, P1 to the 1, because the input degree is 1. This is minus 1 to the z plus, over z plus 1. I expand it as a power series in z near 0, just writing this as inverses of 1 over z because I'm kind of being annoying. And you write down this thing, and then you get a coefficient, which here is a minus 1.
Denis, you mentioned something, but I forgot that if I consider a smooth nearby fiber and look for a vanishing Lagrangian to this one.
Yes. So what this looks like now in the nearby fiber is that A and B both look like a Lagrangian pair of pants inside some C star squared. And this Lagrangian pair of pants need to be wrapped also at infinity. But anyway, so now there's something about the local Floer theory for two Lagrangian pairs of pants inside C star squared. And the claim is that you can reproduce indeed in the wrapped Floer theory of these Lagrangian pairs of pants these combinatorial rules.
Okay.
So that claim now it's an act of faith because it's the only way that things can be self-consistent. I mean, the other option is that one of the two papers I've written recently is completely wrong. But my student Jaewon Chang is exactly checking this, and at least on some simple examples, basically like for very low degrees, it seems to work.
Okay, great.
Okay, so the non-trivial statement is that if you define, so higher compositions work the same now, but with trivalent or with triangles or things like that, but with propagation in the middle. And the non-trivial statement is these satisfy the A-infinity relations. It's actually not so easy to prove because you need to handle this propagation. So there's a combinatorial proof that this satisfies the A-infinity relations. I think I will skip this example. I'm basically out of time. So let me just tell you a couple of theorem. The theorem is, once these categories can actually be calculated, and they are indeed derived equivalent to coherent sheaves on the mirror curve constructed by gluing P1 with 3 points and smoothing as prescribed. So this like generalized state curve. And the proof, in fact, doesn't involve calculating all these propagating things. The propagation is a pain. So I forgot to say something. For example, if I try to ask what are the coefficients of a Floer differential, say, from coordinates here to this y, well, I would have to consider, well, I guess here it started at x1. So I have to consider things where a holomorphic disk propagates through the vertex, then goes here. But it could also propagate through the vertex, then in here, then back through the vertex, and so on. So in fact, all the expressions you get are sums indexed by paths on the graph of components of sigma. And that's not surprising. This is actually how you also write things like higher genus theta functions and so on as sums over the path expansions on the genus G graph. Anyway, but the actual proof of equivalence, instead of brute force calculation, involves in fact a decomposition result. So there's a statement that you can cut this picture in the middle using a suitable Hamiltonian perturbation. Just like in the thesis of Heather-Lee, there's a calculation of the wrapped Fukaya category of an ordinary now smooth Riemann surface from a pair of points decomposition. There's a result that says you can chop things along cylinders by inserting Hamiltonian perturbations. And that way you get models for the Fukaya category, even for this weird one, which are kind of limits, or maybe I should say co-limits or something, of a restriction diagram from this example of mirrors of pairs of pants and restrictions to mirrors of cylinders. So actually how you compare the categories, not by brute force calculation. Right. So I think I should probably stop here. I just wanted to end with a couple of pictures just showing how, for example, a product in this category, mu to a composition. So usual compositions in Fukaya categories involve things with two inputs, a holomorphic disk with two inputs and one output. And that's still the case, but somewhere along the way, there can be propagations happening. So from a computational standpoint, it's actually remarkable. You can get, this actually encodes the geometry of some expansions to express analytic functions and higher genus theta functions in terms of local coordinates. But it's, just enumerating all the cases is actually a little bit of a pain. Anyway, so this is like a curiosity. I'm hoping that sometime a higher dimensional version of this will appear, but I don't have one for now, so I'm not going to tell you about that. Okay, thank you for your attention.
Okay, thank you very much. Really great talk. So questions, please.
Hi, I wanted to ask, this is all built on basically degenerating a curve in some sort of toric variety into pairs of pants, yeah? The mirror formulation. I'm wondering if you do...
That was more the motivation. After this, actually, you don't need it to be in a toric variety anymore, right? Because this algorithm saying, take a non-Archimedean curve near the generalized state limit and build this trivalent configuration of P1s and build a Fukaya category of that. There's no longer a reference to an ambient space.
Okay, yeah. I understood. But in the case when you do have this, there are some nice degenerations where you get these kind of covered P1s, a pair of pants. And I'm just wondering, do you have like a formulation if you had one of these sort of orbifoldy cases, whether you would have a non-trivalent graph or would you have some kind of other structure there? So
the orbifoldy cases depends a bit what's orbifold, right? There are cases where the mirror is this threefold where there's a whole stacky component in the critical locus. That I don't really know what to do with. There's other examples where the mirror indeed has toric orbifold singularities that come from basically, I would say it's from just blindly applying the construction to a non-maximal degeneration. Right. So you can actually do this on a non-maximal degeneration, where instead of decomposing all the way down to pairs of pants, you just go to a nodal union of P1s, but with more than 3 points on each P1. And the mirror to that would indeed be a dual configuration with more than trivalent.
And for you, it's essential that it's trivalent.
No, it's not.
It's not? Okay.
I mean, it is in the paper, but it doesn't really matter that much. So if I'd say decompose, I don't know what I'm going to do, maybe a genus-free curve into two P1s meeting at 4 points. So now, of course, there's cross ratios and things about these 4 points, and there's still my smoothing parameters. That would correspond now to a 4-valent configuration, where, of course, if I had a Landau-Ginzburg mirror, it would have some bad singularities at these 2 points. But I can still do my construction. I would now look at 4-valent graphs on that. And what I would need to specify is the same rule of propagation, but now again using local coordinates near each of these 4 points, choosing basically the 4 points on a P1, choosing, so there's a hidden cross ratio in the symplectic geometry of this weird singularity. There's a cross ratio invariant, which is the choice of where these 4 points lie. And my choice of how to match this with other things involves choices of coordinates near those. The proof of the theorem I haven't checked, but I'm pretty sure the proof of the theorem doesn't rely on anything being trivalent. You can just mimic the definition. It's just that I don't really know what to do with it because I don't like, well, I don't know. I like the trivalent case better just because it's more elegant, but that shouldn't matter. And so that also brings us to the other story that, if you look at higher dimensional examples, you'll have stratified spaces as critical loci with some local models. And the obvious suggestion you see here is what you should associate to each critical stratum is basically a copy of the ring of functions of some higher dimensional algebraic pair of pants or product of pairs of pants, the mirror model, and bases of functions, and then define propagation rules a bit like this. This whole construction really comes from a very naive understanding, in fact, of if I have an algebraic curve built by gluing local analytic charts, and I have a function which is, has some beginning of an expansion in powers of some coordinate on a chart. What happens when I do coordinate changes? What happens when I analytically continue it into the next chart? What happens when I analytically continue all the way around and I come back to the same point? And the answer is this gives like these graph sums over, over paths in my graph that are exactly the formulas that show up in Floer theory. And so if you play explicitly with examples, you see that this actually cannot fail because basically all you're doing is you're embedding the calculus of theta functions into symplectic geometry. And so in that sense, the construction is kind of a huge cheat. It's only because it's close enough to the actual geometry of what you want to do that I think it's really interesting. But somehow, the whole construction is designed so that the thing is going to work for mirror symmetry. So the theorem is almost a bit of a down at the end because, it really says you build Fukaya categories that have local models that are kind of opaque because there's these trivalent things and propagations. But the opaque local model is designed to match the ring of functions on a pair of pants. So of course, by local to global principles, it will produce the right thing.
Gabe, are you happy with the answer?
I'm happy with the answer. I think that the question got changed. So I'm happy with the answer to the question that got changed.
Okay.
I was thinking of something more simple, like, if you take in your elliptic curve case, you degenerate it into 3, pairs of pants, and you can also degenerate, to that other point, and so which it has a, it's sort of a covering of a P1 of a pair of pants, with ramification points at the nodes. And I was just,
yes. So I don't know how to deal with the ramified covering thing. You're saying the ramification versus unramified.
Yeah. So I was just wondering if there's like a trivalent model with maybe some sort of.
So my trivalent model, my favorite one, the one I would deal with easily, looks like this.
Right. And so.
And of course, it has a threefold symmetry, so I could try to then understand whether this can be made compatible with the covering data and so on. I haven't thought about it.
Yeah, that's okay.
There is this in Berkovich book, there is a chapter about non-Archimedean degenerations of curves. You probably should add some orbifold data to what described. I think it's called standard model something anyway.
Oh, okay. So I don't know much about the whole algebraic side of that story. I mean, Efimov educated me as we went through, and kind of.
Yeah. Efimov should know. Yeah. Okay. More questions? Okay. No more questions. Yeah, maybe I ask you a kind of question which is sort of perpendicular to your talk. It's about Landau-Ginzburg model. You an expert. Yeah, I mean, if it's related to something which we are doing with Maxim now, if you replace Landau-Ginzburg potential by a holomorphic one form, like so, what kind of I mean, so you cannot just construct probably the Landau-Ginzburg model just by going to the universal covering and because it can be infinite.
No, but you know. So what do I want to say? Can't I? I mean, can't I just think of it as a Landau-Ginzburg model over a base that has some topology? Oh, not always.
This is another question which is related to what we did with Gabe a few years ago. No, I mean that you do have like holomorphic one form, say with simple poles, like say on the Keller manifold. No, maybe even compact. Oh, like a curve.
I might want a closed one form anyway, right?
Yes, of course, okay. Closed one form, yeah, closed, but not necessarily exact.
No.
Yeah, and even Riemann surfaces produce you a lot of examples.
Yeah, that's a really good question, and I'm not sure what I would want to do because I mean, as you say, there's one option which is to just brute force and go to a cover where it becomes exact. But that feels wrong because that means you have objects of infinite type in there. That I don't know if it feels right or not to have them. I'm not sure that I know how to do. You know, I mean, really secretly, right? In a symplectic Landau-Ginzburg model, the main role of this potential is to declare some direction at infinity preferred and some other direction at infinity forbidden. Right? I mean, the only role, in some sense, of this function in defining the Fukaya category, you know, here we are talking a lot about the critical locus and so on. But if you forget about the critical locus and you ask, you know, in terms of the global geometry of Y, where are Lagrangians allowed to go, where are they not allowed to go? The basic rule is they are not allowed to go towards minus infinity. So the language that's emerging for that is the notion of Fukaya category with a stop. Right. So a stop in a non-compact symplectic manifold is a region near infinity where we disallow Lagrangians from going and we disallow also Hamiltonian perturbations from ever crossing in that region. Then there's a formalism that just starts from the data of a non-compact symplectic manifold and a domain near infinity and associates a Fukaya category to that. And so because of that, I don't care so much about a function. I care mostly about having identified a set of directions where that function goes wrong and I will disallow Lagrangians. So that means now if I try to think of, you know, a one form as a multi-valued holomorphic function, I might run into trouble or not, because the question becomes:
it can be dense.
My manifold, which ends of my manifold have a property that the integral of my one form goes to minus infinity?
Yeah, it can be even if you look for the surfaces, so the behavior can be quite chaotic.
Oh, yeah, yes. It can be completely chaotic. So I think if there are reasonable ways of understanding the ends of a total space, there are some where the integral form goes to minus infinity.
Yeah, I see.
Then I can try to use this constraint.
Yeah, I see.
Not when I really don't know what to do.
Okay. So last chance to ask Denis a question. Well, if not, thank you very much. Really great talk. Thanks.
Thank you, and good night to everyone. Stay safe and see you another time, I'm sure. Yes.
Maybe in person in Kansas.
Yes. Jan, are you coming in November to New York? Or?
Probably not. Virtually.
Virtually. Okay, so I'll see you virtually then.
Yeah. Okay.
Okay.
Okay. Bye. Thank you.